Okay, so the next speaker is Carolina Araujo. Gale Duality, Blowup and Moduli.
Thank you. So first of all, I'd like to thank the Institute for hosting this great conference, and thanks to the organizers for inviting me. It's a great honor to talk in this conference. And I will talk about Gale duality, blowups, and moduli spaces. And this is a manifestation of the Noetherian condition in birational geometry. So I hope to get to there. So first of all, we will always be working over the complex numbers, and I changed the order a little bit. So I will spend most of the time talking about blowups and what I am interested about, and their birational geometry. And then I will introduce later Gale duality as a tool to help us understand these blowups. And then I'll talk about a moduli space, and which is a manifestation of a geometric manifestation of this Gale duality. Okay, so let me start by discussing blowup. So this is the general setup. We will be working with projective. We start with a projective space, and we fix general points in projective space in general position. So for the moment, just think that you pick these points randomly. Later, I can give a precise definition what a general position is. And then we consider the blow up of the projective space at this M points. And the problem that I am interested in is to describe the birational geometry of this blow up. So let me start with a very simple example, which is the blow up of say P2 in 1 point. So this is a very classical operation in algebraic geometry. So basically we replace 1 point of the plane by a P1 of normal directions. So concretely for the case of P2, this blow up can be just constructed as a closure of the graph of the projection from the point from which we want to blow up. So we take the projection, we consider the graph of this rational map, we take the closure, and this is one realization of this blow up. And in this case, so as we will see, it is, at least for surfaces, the blow up of a point is a fundamental operation that plays a very important role in birational geometry. So we can define it, of course, in more general sense. We can blow up any point in any variety. And here, in the case of surfaces, it's important to see, to conversely, to blow down. So when can we blow down? And so if we look at this picture here, so here we replace the point by its P1 of tangent directions. And if you consider the inverse image of this point, so this L, as I said, this is a P1, and if you compute its self-intersection, it is -1. So this is what we call a -1 curve, and it's this classical theorem due to Castelnuovo that conversely, if you have a smooth surface and you find a -1 curve, this -1 curve can be contracted to a smooth point in a smooth surface. So this is, and this actually plays a very important role for the minimal model program in dimension 2. So let me just recall that the minimal model program aims at, given a projective variety X, to find a simplest representative in its birational class, which is usually what we call a minimal model. So in the case of dimension 2, in the surface case, this was developed in the Italian school in the early 20th century. And in this case, this minimal model program is very simple. So what you have to do is starting with your surface S, you start looking for -1 curves. And if you find one, you can just contract this using Castelnuovo's criterion, and until eventually you get to a surface that does not have any -1 curve. So this is a minimal model of your the surface you started with. So this is in this dimension 2 case, it's something very simple. But I just want to warn you that there are some choices that we make here. So we may find many -1 curves, and then we can we must choose which one to contract. So let me illustrate this by again a very simple example of the blow up of P2 at 2 points. So we start with the 2 points P1 and P2, and it will be important to consider also the line joining these 2 points. And then if we blow up these 2 points, then we have these two exceptional divisor, this -1 curves E1 and E2 that appear over these 2 points. But now if you consider the strict transform of the line through the 2 points, of course, this is isomorphic to P1, and you can also compute its self-intersection, which is -1. So this is a -1 curve, and you can choose to contract it. So here so if I start with this surface here, I could choose to contract either E1, E2, or this other -1 curve. And if I contract this one, then what happens is that I get to a smooth quadric. So the P2 blown up at 2 points is isomorphic to a smooth quadric blown up at 1 point. And this surface here already does not have any more -1 curve. It's also minimal. And so this would be 2 different minimal model programs starting with this simple blow up. Okay, so now, so in this case, one can check that these are the only 3 -1 curves in this surface. And so now let's look at what happens with P2 blown up at 3 points. And here I have to choose, I'm assuming I have this general position assumption. In this case here, I just want to assume that these 3 points do not lie on the same line. So if I start with 3 points, so I'm going to represent here the 3 points with, hopefully you can see 3 different colors. And also I want to represent the lines joining any 2 of these points. So if I blow up these 3 points, then exactly as before, we can check that we get, in addition to the 3 exceptional divisors, we get 3 more -1 curves, which are the strict transforms of the 3 lines passing through these 3 points. And then here, so I can, instead of contracting the original exceptional divisors, I can contract the other -1 curves. And what happens is that, again, I get to P2 blown up at, so this is a P2 blown up at 3 points, but this is a different P2 blown up in 3 points, meaning that if I compose this blow up with this blow down, then I get, well, get a rational map, Cremona transformation of P2, which is nothing but the standard Cremona transformation. And okay, and so what I want you to take from this picture is that in this case, the surface, the same surface, has 2 different realizations as a blow up of P2 in 3 points, and they're connected by this Cremona transformation. So in fact, let's look at this. Let's call this Cremona transformation, Q, this Cremona transformation, the standard quadratic transformation. And let's look at this more carefully. So let me introduce some notation here. I will always be denoting by H the pullback of a hyperplane class under a blowup. And I will always denote by EIs, the exceptional divisor over the point PI. So in this case, of course, the Picard group of the blowup is generated by H and the 3 exceptional divisors. So this is a Z4. And it will also be important to consider the Néron-Severi space. So I just tensored this with R, and I have a real vector space, an R4. And now, if I look at this Cremona transformation here, so this is a birational self-map of P2, but it lifts to an automorphism of the blow-up of P2 in the 3 points. And so, in particular, it will induce a pullback, which is going to be an isomorphism of this Néron-Severi space, or even in the Picard group. And it also preserves the intersection form in the Picard group. So here, this Picard group has a natural intersection form given by the intersection product of curves. And so it will induce a pairing in this real dimensional vector space. And this pullback is in fact an isometry. And if you think of this as a linear transformation, this is nothing but a reflection across a hyperplane. And this reflection is very interesting. So for instance, inside this vector space, we have some important cones. We have the cone of Neff divisors. So these are divisors that intersect non-negatively every curve. And we have the effective cone. So this is the closed, the convex cone generated by the classes of effective divisors. So this reflection, it preserves, well, because it preserves the intersection form, it preserves also the Neff cone and the effective cone. And moreover, it maps -1 curves to -1 curves. So it does exactly, it takes each of these minus curves to the opposite one. Okay, so this is for P2 blown up at 3 points, but in fact, the same picture can be generalized for the blow up of any set of points, as long as we have at least 3 points. So of course, here again, we have the similar description for the Picard group and for the Néron-Savary space. And now now I'm in the situation that I have at least 3 points. So now I choose 3 of my M points, say Pi, Pj, Pk, and then I consider the Cremona, the standard Cremona transformation centered at these 3 points that I fixed. Now, in this case, in general, this Cremona transformation will not lead to an automorphism of our blow up X. However, if I only blow up the 3 points that are the center of my Cremona, then this Cremona transformation leads to an automorphism here on this smaller blow up. But the Picard group of this smaller blow up, it leaves as a direct segment of this bigger Picard group. So I can consider the reflection on the smaller Néron-Savary space and just extend it in the trivial way to an isometry of the whole space. So even though this does not extend to an automorphism of X, it does give us an isometry on the Néron-Savary space, which again is a reflection across a hyperplane. But now if I have more points, I can do this for any set of 3 points. And so I collect all these isometries in a group. So this is I call this group W. So this is generated by all the isometries or the reflections that are induced by the Cremona transformation centered at any set of 3 points. So now this is actually a group of reflections. So this is actually very well understood. We're going to discuss this more later. But then what we have is that this acts on the Néron-Savary space as an isometry, and it preserves, as before, it preserves the Neff cone and the effective cone of my blow up, and it maps -1 curves to -1 curves. In fact, one can show that all the -1 curves on my surface are in the same orbit for this action. And so this allows us to produce more and more -1 curves when we increase the number of points. So for instance, then you can check that if you have, as soon as you have at least 5 points, then if you take the strict transform of a conic passing through these 5 points, then it will give you a -1 curve. So it will be in the orbit of any fixed -1 curve under the. So I'll be calling this the Weyl group, and this action, the Cremona action. And so here this is the setup. I constructed this Weyl group that acts on the Néron-Savary space. This is Cremona action. It takes -1 curves to -1 curves. Now this group is very well understood. So this is a reflection group. So these usually they have a Koch-Setter diagrams associated to it. So this is the Koch-Setter diagram associated to this reflection group. And this is very well known that this group is finite if and only if M is at most 8. So what this is telling us is that if I start using these Cremona transformations and I start produce more and more -1 curves, and as soon as M is at least 9, I get infinitely many -1 curves. So this was the original proof of Kodaira, that these surfaces have infinitely many -1 curves. So this is the result. If M is at most 8, then X has finitely many -1 curves. And when M is at least 9, then you get infinitely many -1 curves. So let me go back maybe to my previous slide. So here, So the reflections, the reflection would be the hyperplane that defines the reflection. When I take the points P1, P2, and P3, the hyperplane across which you reflect is the hyperplane H minus E1 minus E2 minus E3. You can write down explicitly. So these are -2 classes then that give you this reflection. You can write it down explicitly. Okay. So here I'm representing the roots. So each one of these roots here, so I define this group by generated by reflections, but it can also be generated in a different way. You can choose a different set of generators, which is you can take some permutations, you just exchange PI with PJ, and one Cremona transformation. And for this, it's easier to see this. So each one of these ones here, this HIs, this would be exchanging EI with EI plus 1. And this here would be the Cremona, the reflection corresponding to the Cremona, the H naught. So this is the exchange E1 with E2, exchange E2 with E3, and so on. Okay, so here we have this characterization, and in fact, it is not a coincidence that if in terms of if you look at the canonical class of these surfaces, in the first case, when you have finitely many -1 curves, this is exactly the case, the del peso case, when the anti-canonical class is ample. And actually, so here, as soon as M is at least 9, that it's not the kx is not ample anymore, but it's actually, it makes sense to divide it into 2 subcases. So there is the case M equals to 9, when the canonical class is, well, it's not ample, but it's at least it is NIF. And then for higher values of M, it is not even NIF. And in fact, there are some differences here. So in the case where M is equal to 9, so this is the effective cone of X. So this is the hyperplane defined by K. This is on the negative side of this hyperplane, this cone is locally polyhedral. However, it does have an accumulation point in the ray generated by -K. And this is, and so outside, so on the negative side of the hyperplane, this is locally polyhedral, and it has this accumulation point. And now for higher values of M, then things are more complicated. In fact, in general, the precise shape of the effective cone is not known. There are some conjectures that predict that this should be a round cone on the positive side of the K, of the hyperplane defined by K. But again, on the negative side, you have sort of this local polyhedral structure. And so I divided it in these 3 cases, because here, okay, this is finite and this is infinite, but this is sort of finite with some order, while for greater M, this part gets very wild, and we don't really understand very well this part of the cone. But for instance, for the case of M equals to 9, so recently my student Luisi Dusso, she was able to find in this case finite polyhedral fundamental domains for both the NIF cone and the effective cone under the action of the Cremona. So still there is some finiteness here that one can exploit to understand these varieties. Okay, so now what I want to discuss is, this is a sort of classical result, but there is a way to interpret this finiteness in terms of a Noetherian type condition. So what we will do, yes. No. I just have to request that they are in general position. And now maybe I can say more precisely what general position is. So the simplest notion of general position is that no 3 points lie on the line. But you want more than this. You want that this condition persists after you apply this, the action of the while group. So after any finite sequence of Cremona transformations, I still want that no 3 points lie on a line. So this is the precise notion of general position, for at least for this case of surface. And now what I want to do is to reinterpret this condition, or to rephrase it, but in a more algebraic way, in a Noetherian type condition. So for that, I need to introduce the Cox ring of my variety of the blowup. So let me do this at least in a more general setup, or at least this is what we need for this talk. So again, I fix a set of m points in Pn in general position. Again, this means that I want them in general linear position, and that they remain in general linear position after a finite and as any finite sequence of Cremona transformations centered at the points. So I take this point, I consider the blow up as before. The Picard group is generated by a pullback of a hyperplane class and the exceptional divisors. And now I define the Cox ring of X. So this is going to be a ring that encodes, it consists of all the sections of all the line bundles on X. So this ring is, so it's possible to define multiplication here. And for that, I actually really need to fix a basis like I fixed here. And then I can define a multiplication as just the tensor product of the sections. And here, this is a graded ring, and it's graded by the Picard group. And for X, the blow up of P2 at m points, it turns out that this was the condition that we were looking before, the condition of finitely many -1 curves, so m at most 8, which is in this case the same as anticanonical classes ample. So this is the same, this is equivalent to the condition that the Cox ring of X is finitely generated. And this is the condition that we are going to use in higher dimensions to understand. And so I will define, let me define here. So this was introduced by Hu, and this notion was introduced by Hu and Kill in 2000. We say that X is a Mori dream space if the Cox ring is finitely generated. And as I will explain to you in this case, when we are in this case, the birational geometry of X is finite, and it can be encoded in some polyhedral structure. So we are going to get there soon. So let me okay. So this is, recall the definition of a Cox ring, and the definition of a Mori dream space. And let me give you some examples. So the first class of example is that of toric varieties. So toric varieties are always Mori dream space. So this was proved by Cox, and actually this is why it has his name. He studied this ring for toric varieties, and it turns out that for toric varieties, this is just a polynomial ring. And conversely, if I have a variety with a polynomial Cox ring, then it has to be a toric variety. But okay, so a different class is that of Fano varieties. So Fano varieties are also Mori dream space, so that is the anticanonical class is ample. And in fact, this is a special case of a stronger result that says that in order to be a Mori dream space, it's enough that it is log Fano. So log Fano, so this appears in the context of the minimal model program. That means that there is a boundary divisor on X such that the pair X delta is KLT, and the log anticanonical divisor minus KX plus delta is ample. So in these cases here, this, as it was proved by Bicard, Caccini, Haken, McKernan in their paper, where they prove existence of flips, they also prove that when X is log Fano, then it is a Mori dream space. And now I want to discuss some consequences of this notion, this finite generatedness. And so if I start with any divisor on X, I can construct the ring of sections of multiples of these. Sorry, here there should be an MD here. So I take the sections of MD for any multiple of D. And if X is a Mori dream space, of course, this is also finitely generated. And then I can consider the rational the rational map induced by sufficiently higher multiple of D. And so these are actually all the contractions on X. So what this is telling us is that if our variety is a Mori dream space, we have finitely many contractions, and they're all sort of encoded in this structure here. So I want to formalize this and to write a precise statement to tell you how we can encode the birational geometry into this finite polyhedral structure. But before I do this, let me work out another example where these things appear in a more or less clear way. So we take now Pn blown up at 2 points, but now n here is now at least 3. And then I consider this blow up, and so this is the same notation I was using before. So H is the pullback of a hyperplane class. I denote by EI is the exceptional divisors. And now I will denote by HI, the strict transform of a generic hyperplane passing through a point PI, and H12, the strict transform of a hyperplane through P1 and P2. So now I want to describe the Neff cone and the effective cone of this blow up. So this is a toric variety. And so in particular, this is a Mori dream space. And in this case, the effective cone is generated by the torus invariant divisor. So it's easy to describe. And now the Neff cone, to look at the Neff cone, now here I'm in dimension at least 3. So now the intersection theory that we naturally have on this variety is the intersection of divisors with curves. So if we want to understand the Neff cone, we can look at its dual cone. So this is the Mori cone of curves. So inside the space of 1 cycles, modulo numerical equivalence, I look at the cone generated by the classes of effective curves. And it's an easy exercise to show, to describe the Mori cone in this case. So this is just generated by 3 rays. So this E1 is just a line contained in the exceptional divisor EI, so E1 and E2, and L tilde, I'm denoting by L tilde the strict transform of the line joining the 2 points P1 and P3. So this is it's an easy exercise to show that this is the Mori cone, and then from this you can compute the Neff cone. So here is a picture. So this is a cross section of the effective cone. So the effective cone is generated by H12, E2, and E1 and E2. And inside the effective cone here, I have the Neff cone of X. So as usual, in the Neff cone, each wall of the Neff cone will correspond to a contraction on my variety. So for instance, this wall here corresponds to the contraction of E2 back to a point. This wall here corresponds to the contraction of E1 back to a point. And this wall here, it is an interesting, it's sort of a different, so this we only see in dimension at least 3. So this wall here corresponds to another contraction, which is the contraction of the strict transform of the line through the 2 points. So one can show that once you blow up P1 and P2, there is a morphism that contracts precisely this strict transform, and it contracts it to a bad singularity. So what we will do here now is we can blow up this P1. So if we blow up this P1, then the strict transform here, one can show that the strict transform over this L tilde is just a P1 cross Pn minus 2. And also one can show that this divisor here can be contracted in the other direction. So I can contract it on the other direction to another variety, X prime, containing a Pn minus 2. And so what I want you to observe from here is that if you compose this blow up with this blow down, I get a birational map between X and X tilde, but this is not any birational map. It has the property that if I remove a subset of codimension at least 2, then it becomes an isomorphism. So here, if I remove this L tilde, and if I remove this Pn minus 2 from X prime, then they become isomorphic. So this is what we call a pseudo-isomorphism. So this is a birational map that restricts to an isomorphism on a big open subset. And now, whenever I am in a situation like this, that I have a variety that we call it as a small modification of X, I can actually identify their effective cone. So because they are isomorphic in codimension 1, any effective divisor on X prime corresponds in a natural way to an effective divisor on X. So they share the same cone of effective divisors. And if now you look at the Neff cone of X prime, you know, it can be seen in this picture, and this is its Neff cone. So this is the Neff cone of this small modification of X. So what we see here in this picture, so this is the effective cone of X, and the colored part, the union of the green and the blue part, so this is the movable cone. So this corresponds to the divisors with no base component, stable base component. So this is the movable cone, and this movable cone is the union of Neff cone, the Neff cone of X, and the Neff cone of a small modification of X. And this turns out that this is a general picture for Mori dream spaces. So now I can state this nice property. So if you have a Mori dream space, then, well, the Neff cone, the movable cone, the effective cone, these are all polyhedral cones. And moreover, there is what we call a Mori chamber decomposition on the effective cone. So this is a generalization of the picture that we saw before. And on this, in this Mori, so this is a decomposition, a wall chamber decomposition. And for this, when you look at the movable cone, this is going to be a union of Neff cones of varieties that are small modifications of X. So in this sense, we can describe all the small modifications of X and all the rational contractions on X by understanding this cone together with this Mori chamber decomposition. And this turns out this is very useful when you want to understand the geometry of a variety. So now let me go back to the blowups, and now we want to understand the connection between blowups and Mori dream spaces. So yes. Do the chambers overlap only in the boundary? Right. Yes. This is really a wall and chamber decomposition. You have some walls, and then the chambers are the connected components of the complements. Okay, so now it is known. So if you here again, I'm always taking points in general position, and I want to understand when the blow up of Pn at this m points is a Mori dream space. And it turns out that this is the characterization. So it's a Mori dream space if and only if it is in one of these situations here. So this was so each direction. So the first direction. So first, what Mukai proved is this first implication. So so he proved that if you have too many points, then it will not be a Mori dream space. And I will say a few words about his proof. And then later, Kastrovet and Tevelev, they proved that conversely, if these inequalities, if these conditions are satisfied, then this is a Mori dream space. And they actually do really. They prove that the Cox ring is finitely generated. So they exhibit generators for the Cox ring. And so let me go back to Mukai's proof. So here again, the idea of the proof is exactly it's the same as the one that I showed you for surfaces. He considers the Cremona action. So if you take, now we are in Pn. So in order to have a Cremona, a standard Cremona, you have to fix n+1 points, and then you can do the Cremona centered at these points. And again, this will induce a it will induce a linear map in the Néron-Severi space. And this is again and they can be collected in a group of reflections. And here now, this is the Kalkstetter diagram associated to this group of reflections. Now here there is a subtle point. The way that I wrote here, you should think of this as roots. And so in the case when n is at least 3, as I said, the usual intersection theory is between divisors and curves. And when I write it here, it looks like I have a lattice structure, some pairing on the Picard group. And in fact, there is. So this is what we call the Cobble pairing. So I learned this from the work of Dolgachev, and he attributes it to the work of Cobble. And so this is a pairing in the Picard group of the blow-up that sort of mimics the intersection theory in the case of surface. So here, the pairing is defined in this way. The h square is n minus 1, dot ei is 0, and ei and ha, this is either -1 if they're the same, or 0 otherwise. So now if you take this pairing here, then actually you can represent this this will really represent some roots for this lattice, and the Cremona action is just the action by reflection on these roots. And so this, and it's very well understood when this group of reflections is infinite, and it will be infinite precisely on the complement of these conditions here. So this is how Mukai proved this. So in this case, you will get infinitely many what he called -1 divisors. So these are divisors that are in the orbit of the exceptional divisors, and all of this will contribute to the Cox ring with a section that must be in any set of generators. So this shows that if M and N do not satisfy this condition, so you have this infinite group here, and then you get non-finitely generatedness of the Cox ring. Yes, I always assume my points are always in general position. In fact, maybe I could mention here that the work of Kastrovet and Tevelev, they allow points in spatial positions. And in fact, what they show is that if you start with any number of thousands, any number of points that lie on a rational normal curve, if you blow up these points, you get a Mori dream space. But for this talk, I am really only interested in points in general position.
I have a question about the theorem.
Yes.
It's also always equivalent to that.
Oh, thank you very much for the question. I forgot to mention this. This is I should have mentioned this before. So the question was whether this is equivalent to the ampleness of the anti-canonical bundle, and the answer is no, for a very simple reason. That line L, that curve L tilde that I considered before, it will never have positive intersection with the anti-canonical. So maybe I go back, I'm sorry for that. Let me just go back to the, should have mentioned this here. So this curve here will have a positive intersection with the canonical if n is at least 4, and in the case of n equals to 3, it will have 0 intersection with the canonical. So this shows that this X here is never funnel. However, if n is at least 4, this other model here, the anti-canonical, will lie somewhere here. And so this small modification will be a funnel variety. And I'm going to now come back to this. So this was my next observation, that in fact, it is not true that this is equivalent to the canonical, to the X being funnel, but later I showed with Alex Massarenti, which is also here, that this condition here is equivalent to X being log funnel. So this is still holds. Yes. Sorry. For the Cobble product. So in a sense, I think this is we're going to discuss this when we discuss Gale duality. Maybe it will be a little bit more clear. But for the moment, this is a pairing, a lattice structure for which the Cremona action will have a nice description as reflection. I don't think I can explain better. I see anything more clear than that. But maybe there is a better explanation. Okay, but we are going to discuss this soon. But let me, before we are moving to Gale duality. So let me just state two natural problems that come from after this theorem. So first of all, first problem is to get a Mori chamber decomposition in the cases where the X is a Mori dream space, to have an explicit description of the Mori chamber decomposition. This will be very useful to understanding the birational geometry of these spaces. And also one may ask, what can be said in the non-Mori dream space cases? So we did say something in the case of surfaces, and can we say something similar in higher dimensions? Okay, so for that, now I move to Gale duality. And so Gale duality is going to be a correspondence that will associate points in a projective space to points in a different projective space. So let me fix here the notation. So I fix two positive integers, r and s, and I let m be r plus s plus 2. So Gale duality or Gale correspondence is going to be a correspondence between sets of m points in PR, always in general position, modulo projective equivalence to the set of the same number of points, but in PS, modulo projective transformation. So before I give so this is defined purely in terms of linear algebra. But before I give the general definition, let me explain the simplest example when R is equal to 1. So in this case, if I call the other dimension n, this is just the number of points is n plus 3. And this is a classical correspondence. So this is just if I start with n plus 3 points in P1, what I can do is to embed this P1 in Pn as a rational normal curve and consider the image of the points. And conversely, if I have n plus 3 points in general position in Pn, there is a unique rational normal curve passing through these points, and then I consider this P1 with this marked point. So this is, in this case, yes? Sorry? Okay, yeah, so this definition works for ordered points, so it will remember the order, but then we can modify it and just consider unlabeled points. But you're right, that this is the way that I will define the correspondence, remember the order, the labeling of the points. So let me give you the general definition. So if I start with m points in PR, I will write the coordinates of the projective coordinates of these points in a matrix. But then, because everything is up to projective transformation, I can assume that the first r plus 1 points are the coordinate points. So this is why I put the identity here. And then I write the other coordinates here in this matrix. So this A here is an S plus 1 cross R plus 1 matrix. And then what I can do is I transpose this matrix. I write here the identity in dimension S plus 1. So now these vectors here, row vectors will be precisely give me the coordinates of these points in PS. So this is how the Gale transformation goes. This, as I said, this is purely linear algebra, but it has some very interesting properties. So for instance, from our point of view, this is very nice because it is compatible with the Cremona action. So what does this mean? So if I start with a Gale dual collection of points, so these are in PR and these are in PS, I can look here at the first R plus 1 points, and I can perform the standard Cremona transformation based at these points. So I will get some new, so these points will be the same. So these points will be the same. And then I look at the image of the original S+1 points here after the Cremona transformation. And then I ask what are the Gale dual of this collection of points. And it turns out that it is obtained on this side by performing the Cremona transformations centered at this S+1 point. So I take the Cremona transformation centered at this point, and these are the Gale dual. So this is, as I said, this is compatible with Cremona action, and this should not be surprising. So let me, if you look at the Koch-Setter diagram that I explained before, so this is the Koch-Setter diagram for the Cremona action on the Néroncev area of this blow up. And if I do the same for the other one, we will see that these two diagrams, they are isomorphic. Basically, there is a reflection in this, the lag here, this lag would be reflected, but otherwise these are the same diagram. And so in a sense, this is a manifestation of the action of the same group. And in fact, so here now I should assume that R and S are at least 2. So if R and S are at least 2, and so here this is a set of Gale dual points, I can consider the blow-ups of this point. So I can consider the blow-up of PR at these M points and the blow-up of PS at the Gale dual points. And of course, one thing is clear is that their Picard group is isomorphic. Of course, they have the same Picard rank. And so the Picard rank is M+1, so they have isomorphic Néroncev spaces. But I have to remember the Cremona action. So it turns out that one can construct a linear isomorphism of these spaces such that, well, so first of all, it takes the canonical class to the canonical class. And this is, so maybe this address is a little the question of change, that this map is an isometry. So if I consider the Cobo pairing, this restricts to an isometry on the perp of the canonical divisor. And so here we really, so in this way, we really see the Cremona action on both sides. And then we are going to use this to, if we understand well one of these blow-ups, maybe we can translate this information to the other blow-up. So this is vaguely the idea that we explore. And for that now, I moved finally to the topic of moduli spaces, because in some cases, at least for now, in the simplest cases, the two simplest cases, this Gale duality has a geometric manifestation in terms of moduli spaces. So let me explain this. So let's first of all, let me remind you, this is the classification of the blow-ups, which are Mori dream spaces. And remember, I posed this problem of understanding the Mori chamber decomposition of the effective cone in the Mori dream spaces cases. And in particular, I would like to address this case here, n at least 5, and I will consider the extreme case here when the number of points is n+3. So in this case, this is if m, so n here and n+3, this corresponds precisely with the Gale duality of between P1 in n+3 points and Pn with n+3 points. And now what we will do is we will realize this Gale duality in a very concrete geometric way as follows. So, so now here I'm in this situation that I fix n+3 general points in P1, and I will define a notion of, I will consider moduli space of parabolic bundles. So in this case, we cannot really blow up the points. And so but we will do something that is morally similar. So we will consider parabolic vector bundles on this pointed curve. So what is that? So a parabolic vector bundle consists of the following data. So E is going to be a rank 2 vector bundle on P1. And for each one of these points, I will also consider a one-dimensional linear subspace in the fiber. So this is the information of the vector bundle, and for each so we call this parabolic points. For each parabolic point, I fix a direction, a one-dimensional linear subspace. And now we will define a notion of stability so that we can construct moduli spaces, and this will depend on certain weights. So I will fix here a weight vector. So a weight can be any real number, any n+3 upo of real numbers between 0 and 1. And once I fix this weight, I get a notion of degree, slope, and semi-stability. So to be precise, the degree of the parabolic vector bundle is just the usual degree of the vector bundle. And then I also add the weights. Now, if I consider, say, a subbundle of E, now I will define the degree. Well, that will be the degree of L plus, but now here I will only add the weights that are respected, for which this line bundle coincides with the parabolic direction. So maybe it's good to have like a picture here. So I'm representing a vector bundle. I will, instead of looking at the vector bundle, I look at the projectivization of the vector bundle. So this is a P1 bundle over P1, and each parabolic direction here is going to correspond to a certain point on the fiber over P1. So you can think of this as once you fix a degree, you can think of this as the parabolic vector bundle. And if I have a subbundle here, this will correspond to a section that will pass only through some of these parabolic directions. And I will only count, I will only add the AIs for those. And then the slope, as usual, you define the degree, you divide the degree by the rank, and this gives us a notion of stability or semi-stability. And then one can consider there is a moduli space for mu semi-stable parabolic vector bundles for any fixed weight vector. And this was very much studied by Bauer in this paper of 1991. So Bauer describes what he calls the weight polytope. So this is a polytope inside this hypercube that parameterizes the weights for which you have an unempty moduli space. And so he defines a chamber decomposition, and this chamber decomposition, so the two weights are in the same chamber if they define the same moduli, the same stability condition, so they will have the same moduli space. And he also described all the different birational maps between these different moduli spaces. And in particular, there is one specific weight for which such that this moduli space associated to this specific weight is precisely the blow up of Pn at the n+3 Gale dual points. So in this sense, the Gale duality in this case is manifested in this geometric way. Here we have a moduli space of parabolic vector bundles on P1 with these marked points, and this is exactly the blow up of P3 of Pn at the Gale dual points. And so I will describe now I will say just a few words about this weight polytope and the chamber decomposition. So this is what we call the demi-hypercube. So this is the polytope whose vertices are, say, the even vertices of the hypercube. So let me just give you just a few examples. So this is going to be too small for us to be interested in, but so that you have an idea of what this demi-hypercube they look like. And so here we have this demi-hypercube. So this is so this is the set of weights for which you have a non-empty moduli space, and it comes with a chamber decomposition. This is just cut out by some hyperplanes. And what Mukai observed is that the effective cone of X is just the cone over this demi-hypercube, in such a way that the Mori chamber decomposition is just induced by Bauer's chamber decomposition. So this is just the polytope, whose vertices are the even vertices of this. So the vertices here, they have coordinates 0 or 1, and I say it's even, say it has an even number of 0 coordinates. Okay, so in this case here, we have this description, and I just want to mention very briefly that this is extremely useful to understand the birational geometry of X. And for instance, whenever n is even, then you have one of the small modifications of X is a Fano variety. It's a very interesting Fano variety. And this has been very much explored to understand the geometry of this Fano variety. But now I want to move to the next case. So this is the last case that we can actually say something. So the case of Pn at n plus 4 points. So in this case here, there is one case when n is equal to 4 and m is equal to 8. This will be a Mori dream space. But as long as n is greater than greater or equal than 5, this will no longer be a Mori dream space. However, we will still be able to say something about the effective cone. So the first case, the case that is a Mori dream space, this was investigated by Mukai. So Mukai introduced these ideas that were later further developed by Casagrande, Codogni, and Fanelli. So they gave a description of the Mori chamber decomposition of the effective cone of X in this Mori dream space case. And then later, together with Ana Maria Castravet, Luise D'Urso, Inderkauer and Diletta Martinelli, we extended this decomposition, this description to the non-Mori dream spaces cases. So I will state more precisely what we say. So this is our setup right now. We have n plus 4 points in Pn, and now the Gale duality will give us n plus 4 points in P2. And again, what we will do is we will have a moduli realization of this Gale duality. So I will call X the blow up of Pn at the n plus 4 points. And S, now it's a surface, is going to be the blow up of P2 at the Gale dual points. And now on this blow up, I fix on X, I will fix some invariants, and I will look at the moduli spaces of vector bundles. So with this invariant, so we fix the rank to be 2. The first Chern class is going to be minus k, and the second Chern class is going to be 2. And if you ask me why, and I can only say that these are the values that work. I do not know why this should be this way, but in any case, in this case here, we can, if you give me any ample line bundle on S, I can consider the moduli space of L semi-ample locally free sheaves on S. And so, of course, this moduli space depends on the choice of the polarization. But in the 90s, this problem was how the moduli changes if you change the polarization. This problem was very much studied by several people, including Getche and Friedman Chin. So these are some of the works that we use. And then if you apply it to this specific case, then what we prove is that there is a choice of polarization for which X, so X here is the blow up of Pn at n plus 4 points, is isomorphic to the moduli space of semi-stable locally free sheaves on S, the blow up of P2 at the Gale dual points. And moreover, we can describe, well, the Mori chamber decomposition, not of the whole effective cone, but at least of the part of the effective cone that lies in the negative part, the negative side of K. And here, this is with respect to the Cobo pairing that I described. So the picture you should keep in mind, so this was the picture for the surface case when you had at least 10 points, and this is more or less the same here. We have now a pairing and then we have a negative side of the canonical class where the effective cone is locally polyhedral and where we actually have a explicitly described chamber decomposition. And well, you have the side where we know nothing about. So this is what I wanted to tell you today. So thank you very much for your attention.
Thank you very much. Are there any questions?
Is there any description of Gale duality that does not require choosing the coordinates on projective?
Sure. It can be. I gave this description because it was easier to understand, but you can describe it coordinate free.
Oh, okay.
So Eisenbud has a very nice paper where he even studied this, and you allow some points in spatial position, and so it can be extended if the points are in spatial position, but not too bad. You still have a correspondence. So he investigates this question.
Yes.
Thank you for the beautiful talk. I have a question about, if you can go back to the slide, to the first theorem with D'Urso about
For the fundamental domain?
Yeah, the fundamental domain. So,
sorry, it will take a little while.
but meantime, I'll say, so a long time ago, the Morrison, we proved the finite fundamental domain for the net cone and the effective cones.
Okay.
But we used the all Veil group. Did you only use the Cremona?
The Cremona group, yes.
Yeah, okay. So that's
Yes. Oh, maybe I want to talk to you about this later. Yes.
So we used everything. I mean, we didn't care.
Okay.
Small. Yeah. Thank you. Yeah.
Any other questions? Yes.
Do you have any expectation to realize the Gale duals of these other cases as moduli spaces of some sort?
That would be, of course, very nice, but I do not know how to do this. So we tried some. We tried some parameters, but we did not succeed. So, of course, it would be very nice, but I don't know.
Let's thank the speaker again.